Be careful about copying these down and make sure you get all the little electrons, make sure you get your bonds in right. What we're going to do is take each one of these properties, define what it is, and then run it through a whole bunch of structures. So you can apply the idea multiple times right from the start. Yes. That was one of the things I was going to ask you, is find which ones have resonance. You take all the fun out of it. Yeah. Anything else got resonance, or is that it? I guess that's it. Yeah, just those two. Well, that's one you can check off the list. We've already identified which ones have resonance. So much for going in order. All right, for these other properties, the first one listed is looking at number of regions of electrons around the central atom. You've got four properties that the first four properties listed have that little black square by them. That's to indicate that those four are inherently linked, no exceptions. So bracket those together. It's not often in chemistry that we get to say there's no exceptions, because there's exceptions to most stuff. But as far as these first four properties go, there's not. The number of regions of electrons around the central atom is the primary thing that determines the geometrical shape. And what you're counting when you're counting those regions of electrons, you're counting neighboring atoms, and you're counting lone pairs around that atom. So for example, on this nitrogen, for nitrogen trichloride, looking at how many different locations around this nitrogen you've got electrons. You've got electrons here bonded to chlorine, bonded to chlorine, bonded to chlorine, and a pair that it's not sharing with anybody, correct? So that would be 1, 2, 3, 4 locations. Electrons are accommodated in 4 locations. How many regions of electrons on the oxygen and water? How many neighboring atoms? 2. How many lone pairs? 2. So 4 locations. Be careful on carbon dioxide. How many neighboring atoms on carbon? 2. How many lone pairs on carbon? None. So just 2 locations. It doesn't matter whether it's a single bond, double bond, or triple bond. You're not counting bonds. You're counting neighboring atoms. So oxygen and other oxygen, that's all you got. There are no lone pairs on the carbon. The carbon is the central atom. You're looking at lone pairs on the carbon. And there are none. So as far as the carbon is concerned, there's only 2 places where there's going to be electrons. That's somewhere over here and somewhere over there. What about this nitrogen? How many total locations? 3. How about the carbon and hydrogen cyanide? 2. This boron? 2. Anybody for 2? Oxygen and chlorine, that's two neighboring atoms, and there are no lone pairs on the boron. So just two locations. This carbon, this nitrogen, this chlorine, 4, this sulfur, this sulfur, and then the beryllium. All right. Question about that? Electrons are all negative and they're going to repel away, and so you're looking at what's anchored around the central atom and how those positions are going to push off from each other electrically. So you count neighboring atoms and you count lone pairs on the central atom. This lone pair here on the back side of the oxygen, carbon never sees that. So carbon's not affected by it. All it knows is there's an oxygen over here, that's one big swarm of electrons, and an oxygen over there. It doesn't have any lone pairs of its own, so it's on the two regions to be geometrically accounted for. Question on looking at a Lewis structure and seeing how many different regions of electrons there's going to be. All right. Next is shapes and bond angles. In something like that beryllium chloride, way over there on the right, when you look at the beryllium as the central atom, there's two locations around it where electrons have to be. And since electrons are negative, they repel each other, they're going to get as far apart as they're able to minimize the repulsion. And so if you think of it geometrically, it really is like the drawing, that if this yellow atom is the center beryllium, then these two perimeter atoms, the chlorines, are going to get as far apart as they can from each other, which will be 180 degrees apart, exact opposite ends. The maximum separation from chlorine to chlorine would be to position them like this, correct? Even if magically you were able to add the chlorine at this kind of an angle, it wouldn't stay that way. Because repulsions being what they are, it's going to push off, correct? So, if you've got two regions of electrons around the central atom, then the electronic shape is going to be linear. And the bond angles are going to be 180 degrees. No exceptions. That's the alignment of least repulsion. So any of these structures that we labeled as being two locations of electrons, go ahead and label them as having a linear electronic shape and 180 degree bond angles. That's all automatic based on having just two regions of electrons. Find all the ones that were two locations and label them as linear electronic shape, 180 degree bond angles. But now if you take that linear structure and you were to add on a third set of electrons, what would happen to this linear structure if I put a third set of electrons here from the top? These are going to repel down and away, correct? To get where it's equal repulsion in all directions. For 3 locations to be accommodated, the best you're going to get would be an alignment like this, where that gives you maximum separation. Electronic shape is called trigonal planar. Planar meaning all the atoms are in the same geometric plane. It doesn't look like it like this, but if you turn it on its side, then all the atoms are in the same plane. So it's triangular with all the atoms in the same plane, and that's going to be 120-degree bond angles. And we start these models around. What's coming around is the trigonal planar model. As it comes around, think about the 120-degree angles, think about that equal positioning. Notice that the central atom is exactly inside the triangle made by the perimeter atoms. The perimeter forms a triangle, and the central atom is in the same plane as that triangle. Trigonal simply means triangular. Planar means even the central atom is in that triangle. They're all in the same plane. Four regions. And this is where it gets a little bit hard to visualize. This is our 3 regions. This is our trigonal planar. And if we took a 4th set of electrons and brought them in, what would happen? Repel, correct? And if that's the kind of the case, then these would repel. This is hard. My coordination is not up to this. It would be something like that, right? What would your angles be? 90 degrees. Okay, don't write that down, that's wrong. But then that kind of makes sense. But what you got to think about geometrically, if that gives you 90 degrees of separation, maybe there's something better. What if the 3rd, 4th set came in this way? Then these would repel down and away from it, correct? That's bigger than 90-degree angles, isn't it? The problem is when you have this other one that looked kind of square-ish, you were trying to keep them all in the same plane. 4 regions is the first time that it puffs up 3-dimensionally. I'm going to pass a model around for this as well. Electronic shape for this is called tetrahedral. And the bond angles are 109.5 degrees. Not 90. But now as this comes around, I want you to do 2 things with it as far as visualizing what it looks like. First of all, think of it as this trigonal planar shape. Think of it as a deformed triangle. But remember that square that we talked about very briefly before I said it was wrong? It's really not quite so very wrong, because if you think about like the 4, my fingers here, the tips of my fingers being the 4 corners of a square, that would be your 90-degree angles. As this thing comes around, think about what it would be if you took one corner of one side of this square and rotated it out of the plane. That's tetrahedral. So as this comes around, picture it, make sure you can picture that as a distorted square. It is a variation on square, but it puffs up the angles from 90 degrees to 109.5. That's more separation, that's less repulsion, that means more stable. make sure you can see visually that this is a distorted square. All of these that are labeled as 4 regions, go ahead and label them as tetrahedral electronic shape and 109.5 degree angles, because all of that is absolute, no exceptions. Next, let's go to the last one on the list, polarity. We're going to label each structure as being either polar or non-polar. Polar meaning you have net positive and negative ends. Positive and negative ends to the molecule, which really means electrons are not distributed symmetrically. This is all about symmetry. So that's the technical definition. The practical definition is this. In order to be non-polar, you've got one of 2 criteria. One, it's just carbon-hydrogen. If all you've got is carbon and hydrogen, their electronegativities are almost equal. And so if that's all you've got is those 2 particular elements, then shape don't matter. The bonds are very nearly equal, 50-50 sharing, that's considered non-polar. But if it's anything else, then you've got to look at it in terms of symmetry. If everything is perfectly symmetrical around the central atom, if it's equal bonding in every direction, then it will be non-polar. But if it's any kind of lopsided, it'll be polar. Polar means not symmetrical. Non-polar means that it is symmetrical. When you look at NCl3, and we've got electrons in 4 different locations, are all 4 locations identical? No, we've got chlorine, 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 and nothing, right? Since they're not all identical, this is not symmetrical, and therefore polar. H2O, polar or non-polar? Polar. CO2, polar or non-polar? Non-polar. Non-polar. There's 2 locations and they're both oxygen, right? So that's exactly equal bonding in both directions. The electrons are not skewed in favor of one oxygen or the other. It's perfectly equal bonding in every direction, therefore non-polar. NOCl, polar. HCl, polar. BOCl, polar. COCl2, NO2 negative. You got a lone phase there, so polar. Now, those two oxygens are equally bonded, right? But that's not in all three locations. What about the perchlorate ion? That one is nonpolar. And it's the resonance that makes that equal bonding in all four directions. The drawing looks like three of them are double bonded and one is not, but you know better. That's resonance. That really is equal bonding to all four, therefore nonpolar. Go ahead.
Can you explain how, like, although they both have resonance, why one's nonpolar and the other is?
Because this is, the resonance makes this equal bonding in every direction. Whereas this is equal bonding in these two directions, but this one also has a lone pair. So that's not, for the NO2 negative, that's not equal bonding in every direction. There's three locations, and only two of those involve oxygen. Is that any better?
Mm-hmm.
Okay. Sulfur trioxide, nonpolar. SO2Cl2, polar. Now this is one where you have to be careful, because the way it's drawn on the board, it looks like one oxygen is right across from the other, and therefore they would offset. The two chlorines are directly across from each other, and therefore they would be offsetting. But wherever those models are, take a look at the shape. Are there any offsetting positions in this? No. What's on the board there is what's called a bad or deceptive drawing. Not that I would ever do that to you, but expect it all the same. All right? It could accidentally happen on the test. Remember, Lewis structures are not meant to imply shape. It's a step you go through to figure out shape. And so even though what's on the board is a perfectly valid Lewis structure for SO2Cl2, it does not imply that these oxygens are in offsetting positions or that the chlorines are in offsetting positions. Tetrahedral has no offsetting positions. That's a two-dimensional drawing of a three-dimensional structure. And that's where it comes in handy for you to be able to visualize this and know that in that tetrahedral framework, there's no opposing positions. If this tetrahedral is going to be nonpolar, then all four sites have to be identical. SO2Cl2, are all four sites identical? No. Therefore, that's polar. Two of these positions will be oxygen, and the other two will be chlorine. And there is no offsetting vector forces or anything like that. Question about that? Put a little star by that one, because that is a very common mistake. And I will very likely give you the opportunity to make that mistake on the test, so don't fall for it, all right? That drawing does not imply actual shape. You have to think three-dimensional. And it helps to just know outright that the only way for tetrahedral to be nonpolar is for all sites to be the same. If all four of those perimeter atoms were chlorine, then it would be nonpolar. If they were all four oxygen, it would be nonpolar. But any kind of mix and match going on there is going to be polar. All right? And BeCl2, nonpolar. Any question on polarity? What to look for to determine if it's polar or non-polar? Question? All right. Now the next three that we're going to go through are the sigma bonds, pi bonds, and orbital hybridization. And these are ones that are a whole lot more complicated to explain than they are to apply to the structure. So let's start with sigma and pi bonding. Sigma is Greek letter for S, pi is Greek letter for P, and S and P are orbital types. So you would be right in suspecting this has something to do with orbital shapes and how orbitals fit together to form bonds. Shapes of orbitals. S orbitals are perfectly spherical. They're just round, three-dimensionally round. So I'll just draw that on the board like this. P orbitals are more of a figure-8 shape, which I'll draw on the board like this. D orbitals are more of a cloverleaf shape, something like this. And let's just say F orbitals are too complicated to draw, all right, and leave it at that. I'm not even going to try to draw those. There's kind of like two of these clover leaves, off kilter and inflated out. Right? So just trust me, they're complicated. But these are the ones that we'll deal with frequently. And that's the inherent shape of the orbitals. Now, a sigma bond is defined as direct overlap of atomic orbitals in a single location between the nuclei of the atoms that are bonding. And this is, at least so far, what we've talked about as far as covalent bonds. If this is an s orbital, and this is an s orbital, then when those orbitals come together, you get overlap of the orbitals, where here's a nucleus, here's a nucleus. You get overlap of the orbitals in a single location, and that's where the sharing occurs, directly along the line between those nuclei. Sigma is defined as direct overlap in a single location between the nuclei. And so what's drawn there is a sigma bond formed by two s orbitals. This would be a sigma bond formed by two p orbitals. Here's a nucleus, here's the region of overlap directly between those nuclei. Direct overlap, single location between the nuclei. This would be a d orbital and an s orbital. Nucleus, nucleus, single location between them. Notice the definition of sigma bond has nothing to do with s orbitals. You don't have to have an s orbital. But it's named after S because of your four orbital types, S, P, D, and F, it's simple enough in form that even an s orbital can achieve it. It's named after the simplest type of orbital that can form that kind of bond. This is direct and simple enough that even an s orbital can do it. And therefore it's named after S. Pi bonds are less direct. pi bonds, you're having overlap in two locations. Not in the plane of the nuclei. And so that would look something like this. If this is a p orbital, and we brought in another p orbital parallel to that, and here's a nucleus, and here's a nucleus, but the electrons are out and around. If those orbitals come in parallel, then those electrons that are being shared where the orbitals overlap is not directly between the nuclei. It's two locations above and below the plane of the nuclei. That's less direct than a sigma, and that also, I guess, means it's less strong. What's on the board is a pi bond formed by two p orbitals. This would be a pi bond formed by a d and a p. Or two d orbitals. But there's no physical way you could bring two s orbitals together and have them overlap in two different locations, correct? Geometrically, it's not possible to take two s orbitals and bring them together and overlap in two locations. So p is the simplest type that can achieve a pi bond, and therefore it's named after p. Sigma bonds, S, P,